Okay, so these are a few problems, concept questions, and other types of problems from chapter 2, which is about energy and forms of energy and some of the transformations between these forms of energy. So some of the concept questions that I recommended you look at in the text are the following. So you consider falling rock off of a cliff into seawater, and eventually this rock is settling on the bottom of the sea. So starting with the potential energy, identify the energy transfers and transformations involved during this process. We talked about this in class. If the potential energy is maximum on the top of the mountain, and then you have the water here, then there is some transformation between potential energy into kinetic energy, and then kinetic energy into maximum kinetic energy before impact, and some of it goes into deformation, so deformation of the rock, or if it's not a rock, it's like elastic material, and this will eventually translate into thermal energy, in addition to friction between the rock and the air as it falls, and many other types of energy once it settles down. So but basically transformation between potential and then kinetic energy, and then eventually everything will be left off as a thermal energy or internal energy increase of all the components. Then there's another question: what's the difference between macroscopic and microscopic forms of energy? We said this is for the whole system, so like kinetic or potential energy, and these are the constituents of the systems, like atoms when they vibrate, or when they spin, or when they translate or bump into each other, like the atoms or the fluid, or the molecules or fluid, and all the rest. So this is for the whole system, and this is for the atoms or components of the system. Then what is the total energy, and identify different forms of energy. We already talked about this. Total energy is composed of internal energy and then kinetic and potential energies. How are heat, internal energy, and thermal energy related to each other? Well, this is important. We said that heat and work transfers are boundary phenomena, so they're only recognized as they leave or enter or enter the system. So they're recognized at the boundary. So the system cannot contain heat. They eventually translate into internal energy, and if this internal energy can be measured with a thermometer, then this is a thermal energy. Or if they raise the temperature, it's a thermal energy, and if it contributes to dissolving the chemical bonds between the molecules or the atoms, then it could be a latent energy. So they're all thermal energy, and thermal energy is part of the internal energy, and the internal energy, along with nuclear energy and chemical energy and all that, these are what constitute the internal energy. So these are properties of the system, and not like heat, which is an energy in transit into or out of the system. Then says, what is mechanical energy? Was part of the total energy that can be translated or transported or transformed easily into mechanical energy. So that includes, of course, kinetic and potential energy, as well as the mechanical energy contained in like a pressure differential between the system and its surrounding. So it differs from the thermal energy, of course, because if you have thermal energy, internal energy, and heat, and all this that goes on for the single or multiple atoms, then it doesn't help me to move things around. Unlike mechanical energy, which you can translate easily into something that could be used more useful. What are the forms of the mechanical energy or fluid stream? This is the kinetic energy, potential energy, as well as the pressure. This is, if you are into mechanical or chemical engineering, this is what you do later, or civil engineering. This is what you will discuss later as the conservation of energy, and then it will give rise to the Bernoulli equation, which is just an expression for the mechanical energy of a system, of a flowing fluid. Then, in what forms can energy cross the boundary of a closed system? Closed system, so no mass transfer. It's not an open system. It's not a controlled volume. So this is a controlled mass. So mass cannot get in or out of the controlled volume or closed system. So just heat and work. That's easy. And then when is the energy crossing the boundary is cross system is heat, and when it's work? Well, if it's the result of a temperature difference, then it's heat. Otherwise, it's work. So compression of a gas in a piston cylinder device, that increases the energy, but not a function of, or not a result of a temperature difference. So it's work, called like a boundary work. Or if it's a result of conversion of electrical energy into internal energy, then it's work. If it's shaft work, and so on. So if it's as a result of temperature difference, then it's heat. Otherwise, it's work. Next, it asks, what is an adiabatic process? Well, there is a adiabatic process, of course. Where the process where no heat is transferred. Okay, so this one, this Q, as we call it, is equal to 0. So that doesn't mean that that there is no temperature change. I can have an adiabatic process where I insulate the thing pretty well, and then I could add energy using like boundary work. So the temperature will increase as a result of this compression, but not as a result of heat, but as a result of work. So this boundary work will result. Or I could run like an electric current here, and then it's adiabatic, so no energy or no thermal energy crossed the boundaries, but the temperature changed. So adiabatic does not mean, in general, okay, in general does not mean isothermal. So adiabatic is not usually means isothermal. Okay. And then what are point and path functions? We said that like point functions depend on the location of the thing, like a location on the value of the property, and not on the path it takes. So if you go from 1 to 2, it's just difference between these locations, like the x location. Okay, so x and y. So delta x, delta y are constant regardless of the path you took to go from 1 to 2. However, the work and the amount of heat transfer are path functions. So that's why we say du, but and delta kinetic energy and whatnot, and then we say that we have like a delta. Small delta, lowercase delta for a Q and for work W, because W and Q, work and heat, are path functions. Okay, like heat transfer and many other examples. What are the caloric theory? Well, we talked about this in class. In the old days, like 150 years ago, it was thought that energy was this massless, colorless, weightless, whatever fluid, and it's called the caloric. And that when some temperature of a system increases, it's just a transfer of this liquid. Right? It's if you look history, look at it and see. Now the new heat theorem and the new thermodynamics is much more useful. Consider an automobile traveling at a constant speed along the road to determine the direction of heat and work interaction, taking the following systems, the car radiator. So there is a you want to look at the heat and work interactions, taking the system sometimes at the car radiator. Of course, there's no work in radiator, just flows, something flows in, water flows in, and there's a fan that cools it. So there is maybe some boundary work, some flow work coming in, but usually mainly it's heat that's coming out, transferred between this fluid and the air, surrounding air. The car engine, same thing, but the difference is, well, yeah, I mean, it's hot, there is heat transfer from the hot surface of the car engine to the surrounding air, but more importantly, there is some work, there is some power for the engine, the internal combustion engine. The car wheels, there's maybe some minimal heat transfer between the wheels and the road, but not much is going on. Same for the road, so they are not moving past each other, so no boundary work and no nothing. They're not doing any work because they have force applied to them, but this force is not moving anything. And air surrounding the car might receive some cue because of the hot car and hot engine, and maybe the friction from the car between the wheels and the road. Maybe that's they gain some minimal amount of thermal energy. The length of the swing can be changed by applying a force or changing its temperature. Yeah. So what type of energy interaction? If you compress it, then it's a work interaction, and if you change its length by changing its temperature, then it's a heat interaction. A car is accelerated from rest to 85 kilometers per hour in 10 seconds. So would the energy transfer of the car be different if it's accelerated to the same speed in 5 seconds? Well, the total energy is asked about the energy. Okay, so the energy is kinetic energy. So from 0 to 85. So this kinetic energy is 1/2 m v squared. V2 squared might be what? There's no mention of the time. However, if you look at the change in the kinetic energy with respect to time, then you would this change of the kinetic energy times delta t, which will give you the power that expended by the car, and this depends on the time. So the amount of work, compare it to yourself. You're doing the homework in 3 days. So you're doing the same amount of work that a student that did the work in 2 hours. However, they have more power, they're more powerful than you. Okay, maybe this is a bad example. For a cycle, is the net work necessarily zero? For what type of system? Well, this will be the case. If you remember the cycle where you leave and come back to the same position, so you go from state 1 to state 2, state 3, and then finally and then you come back. The amount of heat transfer and the properties, the changing properties, they cannot change. However, if you look at work, for example, the boundary work, the area under the curve, this PV, so this is PV, this is different than this guy. So there is the difference here can be net work out, for example. Or if the work in is greater than the work out, then this is the net work in. I hope this is clear. Okay, on a hot summer day, a student turns his fan on when he leaves the room in the morning. When he returns in the evening, will the room be warmer or cooler than the neighboring rooms, and why? So you assume that all doors and windows are kept closed. So this is the room, and this is your fan, and this blows air. If this is sealed, it says all windows, doors are kept closed, And let's assume, for the sake of argument, that this is well insulated. Well insulated does not mean that Q here is 0, and it does not mean that there is no electric power coming in. So this is this gets some electric power and it moves air around. If you look at the change in the energy, there is no heat, but there is work. So, and the change in energy in the higher, it will be translated into not kinetic energy and potential energy, because this is stationary, but internal energy. So I'm adding work, it will increase, okay, no matter what. It might, the temperature here, if you're standing here, due to convection and the evaporation, if you're sweating, you might feel a bit colder, but eventually, if you average everything in the room, this motor will transfer some of the electric energy into heat. Okay, it will dissipate. Lastly, what are different mechanisms of transferring energy for control volume? Open system. So instead of in addition to the work and heat, you have mass. So heat, work, and mass. Heat, work, and mass. Okay, so let's look at a couple of examples. You have a classroom that normally contains 40 people. To be air conditioned, we want this to be air conditioned with window air conditioning units. So window units, 5 kilowatt cooling capacity each. So at the end, we want to see how many of these we need. A person at rest may be assumed to dissipate heat at a rate of about 360 kilojoules per hour. First, we read the problem together. So 360 kilojoules per hour, and there are 10, and you said there are 40 people, and there are 10 light bulbs, each with a rating of 100 watts, so 100 kilojoules per second. The rate of the heat transfer to the room through the walls and windows is estimated to be 15 kilojoules per hour. So if the room is to be maintained at a constant temperature of 21 degrees Celsius, determine the number of window air conditioning units. So what happened here is that the bulbs, light bulbs, and electric energy coming in, so they emit this energy that comes, this 100 watts. Eventually, if you give it this electricity, it will be heat. Okay, so you have heat from the lights and heat from the people. Okay, they eat food, and the chemical reaction in their cells, so they also emit heat, or emit thermal. There's conversion to thermal energy, and you have 40 of them, and you have what else you have? Heat is transferred into this at a rate of through the windows and walls and everything is 15 kilojoules per hour. So if you change it to second, you'll get in watts. So we want the total heat addition Q from everything plus the heat generation, so energy generation within the thing. And this has to be equal to the energy removal if we want to say that delta E or delta U of the room is 0, okay, or the rate of this with respect to time is 0. So no change in the internal energy of the whole room. So it doesn't matter, you leave it at 21 or 121, because if you seal it with no air condition, they will melt. Okay, the room will melt because you're just injecting heat. Because I told you, the heat transfer, no matter what, this is the power you'll get, and no matter what, this electricity will flow in. It will melt everything, and it doesn't matter if this is 1,000,000 degrees Celsius. You're still putting it this 100 watt. Same thing, they will burn, but they'll still give you this thing, theoretically. So what do? You collect them and you pay attention to units. Okay, you pay attention to units. So let's say the heat addition to the room, you have 40 people times times you have 360, assume to dissipate, sorry, this, so 360 kilojoules per hour, and you have 1 hour, that is 3,600 seconds. So this will give me kilowatt. Plus, so 40 of them, plus 10 light bulbs, so 10 light bulbs, each emitting 100 watts. So 10 times 100 watts, and watts, 1000 watt is 1 kilowatt. Okay, so this will give me kilowatt, this will give me kilowatt. And what else you have? You have heat transfer from everything else, the parameters. So this is 15,000 kilojoules per hour, and yeah, just 15,000. And you have 1 hour is 3,600 seconds. So you'll divide this by 3,600, and so you'll get kilojoules per second, which is kilowatt. So when all of this is said and done, and this does not factor in, مهم إنه constant proper, so you want delta U to be 0. When all of this is said and done, this will give you, for example, if it's like 5.1 kilowatt, then you'll say I need almost 1. Okay, only 1 هذا, it's fine, we neglect. If it's 6.9, well, it's middle of the road, I would get 2. If it's 9.8 kilowatt, then I need 2 of them. Okay, if it's 10.3, I'll get 2 again, so kilowatt. The heat addition, kilowatts. And one of them will remove 5, so I'll just suffer for 1 hour. Is safe 1 hour or half an hour where everything is at maximum power. So this is how we do it. This is from the book. Then another example is an adiabatic closed system. So what does this mean? Adiabatic closed system, no heat transfer and no mass transfer, is raised 100 meters at a location where the gravitational acceleration is 9.8. So I have G, and I have delta Z, okay, 0.81, and this is 100 meter. Determine the change in energy of the system. So it didn't tell me anything about delta T, delta kinetic energy, nothing. So I'll just say the change in energy is of the system, just a change in potential energy, and I have no information about the mass either. So this is energy. This is P E. Okay, and this is just G delta Z. So G delta Z. So this is 100. Okay, so 900. This will give. This is 9.81, and this is 100, and this will give me 9. This is 9.8, 981. Yeah, so 981. Units. This will be kilojoules. This will be joules per kilogram. Well, this is joule. This will be kilogram meter per kilogram meter per second square. So this is meter square, sorry, meter per second square, and this is meter. So this is meter per, I don't know. المهم ان this one is not kilojoule, this is joules per kilogram. Okay, I'm doing the per unit mass per kilogram, so this is joules per kilogram. so this I have to divide by or multiply by 1 kilojoules, okay, over 1 kilojoules is 1000 joules. So I have to divide by this, and this will be 0.81, I think. Okay. Next, you have a question about how much work in kilojoules, again, can a spring whose spring constant is 3 kilonewton per centimeter, don't forget, can this spring produce after it has been compressed 3 meters or 3 centimeters from its unloaded length. So if you have x0 and x1, make sure that this is 0. If you want to compute not the force but the work, and pay attention to units. So it's asking me about the work. Okay, how much work? So we know that work for the spring is just for anything is just F ds from state 1 to state 2, and for the spring F is equal to x or kx, the spring constant, kx times displacement. So this is the integral from 1 to 2 kx, and this thing is dx, okay? And this is nothing but I'll take this outside, and this will be k, and this is x squared over 2. So if you evaluate it, this will be k over 2 x2 squared minus x1 squared. And from the unloaded position, so this is 0. And again, pay attention to the units. If this k is 3 kilonewton per centimeters, this is I can convert it to meters. So 300, so I multiply this by centimeter, so there's 1 centimeter, 100 centimeter, 1 meter, so this will be kilonewton per meter. And then this guy, this is 3 centimeters, so in meters this is 0.03 centimeters squared, that's 0.03 meters squared, so meter squared or meter squared, so this will be joules. So kilonewton اللي هو kilonewton meter, so this will be kilojoules. So this is I don't know. Okay. So this is meter, and this I converted to meter. This I converted to meter by multiplying by 100. يحرك لي 3 kilonewton per centimeter، يحرك لي 300 kilonewton per meter. Yeah, that's it. Let's turn to kinetic energy, for example. Or potential energy, right? There's an angle. So you want to determine the power required for 2000 kilogram car to climb a 100 meter long uphill. So this length is 100, and in 10 seconds. So delta t is equal to 10 seconds, and this guy is 100 meters, and this guy is 30. So this guy is 100 sine 30, which is 1/2. So this is 50 meters. Then sine 30 is 0.5. هذه square root of 3 over 2. Okay, so this is this is 50. So the climb, if you need to do potential energy, delta z is equal to 50 meters. Okay, again, never forget joules والكيلوجولز اللي شفناهم مساء. Okay. So we want the power. So this is why it gave us the time at constant velocity. So when you have constant velocity, let's see what the contribution to this power is. Some contribution from the gravitational component, and some contribution from the kinetic energy, the thing. Let's call it the acceleration. Okay, acceleration, and this is gravity. So this has to do with the potential energy sort of thing, and this has to do with the kinetic energy contribution. So when I say at constant velocity, well, let's write this in the general form. I could say this gravity would be G Z2 minus Z1. This will give me the work, the potential energy increase. If I divide it by the delta T, it will give me the power contribution of to the total power of the potential energy, the raising of, remember we talked about raising a body in a gravity, or accelerating a body, the work done against gravity, plus some component for the acceleration, so accelerating kinetic energy, so 1/2 m اللي عندنا v squared, v2 squared minus v1 squared. This will give me, this will give me the kinetic energy. So this will give me kinetic energy. I want the power, not the energy, so I have to divide by this. Note that this will give you these. If you substitute these numbers, this will give you in joules. So if you want it in kilojoules, you will have to, or kilowatt, the power in kilowatt, you have to divide by 1,000. This will give you in watt. Sorry, my bad. Okay, so I have to divide by 1,000. So that's it. So for case A, you'll have constant velocity, so v2 equal to v1 here. So this contribution is 0, and this total power is equal to 9.81 times z2 minus z1. The difference is 50, we said, divided by 10 seconds, and this will be in watts. So in watts, and I have to multiply by kilowatt, and this will be 1,000 watts. So this will be, I don't know what. In the second case, you have from rest to final velocity of 30 meters per second. So still you're climbing up. However, you're increasing in your velocity. So the total power required to do both, to work against the gravity as well as accelerate the body, this will be the same, right? So this will be اللي طلعناه من هنا, so 9.81, and the same work done against the gravity. So this is 50. And this is divided by 10, and this is multiplied by 1,000, because 10 seconds from rest to final velocity doesn't say it climbed higher, but now we have the contribution of the kinetic energy, because acceleration, so 1/2 m, the final velocity is 30, so 30 squared minus 0 squared divided by delta t, 10. Okay. If you want, you could divide this by 1,000 to get it in kilowatt. C, from 35 to a final velocity of 5 meters per second, disregarding friction and everything else. So this will be same thing here. Okay, same guy. However, this will be 1/2 m. The final velocity v2 is 5 squared, and then this is 35 squared. divided by 1000 everything. So you notice in this is minus, so this is very big, and this item will eat this component, so in the higher like minus. So this is a deceleration. Okay, so so basically you're braking, you're braking your car. I mean, you're holding the brake. This is again something about efficiency, which we discussed very briefly. You have 90 horsepower. You can convert horsepower to electric kilowatt. So if you need to memorize this is HP. 1 horsepower is 0.746 kilowatt. Okay, you can look it up, or you can just memorize this. So you have a electric car that has this shaft power. It's a very weak car. This is powered by an electric motor mounted in the engine compartment. So electric car ممكن تكون مثلا قطار ولا golf cart. Okay. If the motor has an average efficiency of 91%, so the motor, you have electric power into this motor, and it gives you like a kinetic or shaft work it has a 90 with a 91%. So if you want an output of 91, you'll give it 100. Okay, you give it a little bit more than what you need, because it's not 100% efficient. Okay, we started this. This is the desired output over required input. So required input is 91. So the desired output, if this 91, so you have to multiply by a higher number than this. Check the equation we looked at. So the motor has efficiency 91%. Determine the rate of heat supplied by the motor to the engine compartment at full load. Full load. نشوف full load means. But let's look at this problem. Work for the electric motor. Electric motor is nothing but the shaft work divided by the efficiency. Okay, so the electric work, if you want 100 or 90 horsepower, you have to give it more than 90 horsepower. Okay, like we said, efficiency is desired output over the required input, اللي هو input. Okay, so هذا الشافت. So switch these and I'll get this. So 90 horsepower, so the electric input is 90 divided by 0.91 اللي هو whatever. Okay, so this is the electric work input. If you give it this much energy, if you give the electric motor this much energy, it will give you shaft power. If you give it 90 90 divided by 0.91, so this is 98.0 almost. Okay, so 98.90 afwan. So this is 98.90. What is this in units? Horsepower. So this guy tells me, and if you want your electric car shaft power to climb whatever. This motor is not 100% efficient. You have to give it 98.1. So you have to give it like 10% more, almost 10% more power, for the electric motor, so that it gives you this much shaft power. You have to give it 98.9 horsepower so that you get out of it 90, because you need 90 to climb whatever. It's electric, this golf cart or whatever. So where does the rest of the input energy go? It goes into heat. The inefficiencies, في friction between the parts of the motor or whatever, في يعني imperfect combustion or expansion or contraction or whatever. So this is what the heat supply by the motor to the engine compartment. So هذا الengine compartment this electric motor is giving this shaft power. وين الباقي يروح كهيت, dissipation heat. So basically 98.9 minus 90 horsepower. So this is 8.9 of horsepower. هذا الheat dissipation. If you multiply it by 7.46, this will give you, I don't know, so 8.9 horsepower times 0.746, 1 horsepower. So this will be, I don't know, 3/4 maybe 0.6 something, whatever, or 6 point something, okay? Kilowatt. So this is the heat supplied to the room due to inefficiencies. Okay, about 10% of the power generation. Lastly, let's look at this last question or last example. I don't know how much we took. قصر الفيديو قدر الإمكان. This guy tells me water is being pumped from a lake to a storage tank 20 meters above the lake at a rate of 70 liters per second while consuming 20.4 kilowatt. So this pump is getting some energy in, and it's doing some raising the potential energy of this bulb of water by about 20 meters. Okay, so that's what it's doing. We want to disregard any friction and losses, so no efficiency issues. Friction and losses disregarded in the pipes, and any change kinetic energy. So this was a low velocity, it puts it out as a low velocity, so no kinetic energy and no friction, so no internal energy changes. مو ياخذ بارد يحطه حار. Some of the pumping power went to the internal energy. No, so no friction and no kinetic energy changes. We want to determine the overall efficiency of the pump motor unit and the pressure difference between the inlet and exit of the pump. So what do? You have this rate. So this is m dot, which is, let's get it in terms of like kilograms per second. 70 liters, a liter malma is 1 kilogram, so this is almost 70 kilograms per second. Assuming one density is 1000. So that's m dot, and then we want to see the change in potential energy that this pump is negotiating. So the difference is this potential energy delta PE is G delta Z, it's per unit mass, TZ. So this is 9.81 times delta Z اللي هي شنو delta Z 20. And this will give you units, it will give you joules. So if you want in terms of kilojoules to be consistent, I have to divide by kilojoules. هذا راح يعطيك something. Okay, so you have the change in potential energy that is required to put into the water. So you know that, well, we have to do the numbers. عندنا رقم هنا الefficiency, عندنا رقم consumption. So let's crunch these numbers. 1 second. 1.81 times 20 divided by 1000. So that's مو معقول. Yeah, yes, that's it. معقول. So 0.1962. 1962. شنو هذا؟ كيلو جولز ولا kilojoules? This is kilojoules per kilogram. هذا per unit mass. So per kilogram. If you want to look at kilojoule per kilogram, if you want to multiply it by m dot, it will give you a kilowatt. So let's do this. Let's say if you multiply, the change in the energy of this is ماكو delta U ولا كو delta KE plus delta PE. So these are neglected. So the change in and if we power, so delta T وهني delta T ماكو delta هني ماكو delta. So basically E dot is equal to PE dot. So M dot PE هذا ماله. So 70 and 70 kilograms per second. So 70 times this guy, 0.1962, and this will be times 70. So this is 13.734. So 13.734. Maybe 73. That's أحسن. So this is kilowatt. So this is the mechanical energy needed to do this straight up. How much is it getting? This is the desired output. شنو required input to do this job? This consumes 20.4 kilowatt. So this is for the mechanical energy. So this is both the pump motor, say pump motor, that's it's asking, pump motor unit is the desired output over the required input, اللي هو desired output هنا 13.734 divided by 21 or 20.4. Okay, times 100 هيطلع كم هذا على هذا 0.7 around whatever, or 70%. We multiply it by 100, around 70%. You do the thing. Okay, so this is part A, and then the pressure difference between the inlet and exit of the pump. How do you do this? Pressure difference, هذا mechanical energy. So if you consider the pump, هذا بالنسبة من هني لهني. I consider this whole thing. If you consider the pump من هني لهني, يعني من هني إلى هني, between inlet and exit of the pump, the only difference is the mechanical energy. So there is no kinetic energy. They said kinetic energy, internal energy, كلها negligible. So it's only the pressure. So how do you do the pressure? The pressure difference. It's just the whole thing is so mechanical. If you remember this mechanical, E mech is equal to P over rho plus kinetic energy plus potential energy. Potential energy. But we're not considering the whole thing. We're just considering من هني لهني. So difference is this. لا kinetic energy ولا potential energy, is just this. So basically B, this is A. So B, you have the mechanical energy, for the pump for the fluid is just m dot اللي هو 70 times delta p اللي هو delta E اللي هو energy in mechanical energy in minus mechanical energy out ماكو dot is equal to m dot delta p. So this mechanical energy I know what it was اللي هي هذه so delta p will be pressure difference is this mechanical energy divided by m dot. This will be 13.734 divided by m dot اللي هو liters per second. I don't want liter per second. This is rho اللي هو v dot. So v dot اللي هو 1000 kilogram is 1 cubic meter. So this is 0.070 meter cubed per second. And this will be, I don't know, هذا 10% من هذا. It's around 20 لا, around 200 kilopascal. So this is the difference in pressure. بس I'll stop here and cut the video short عشان ما نطول. بس